So I'm Iunio Iervolino, I teach earthwork engineering and structural dynamics at the University of Naples Federico II, and today I will show you briefly what we have, the issues and the policies that we have in place for earthquake risk reduction in Italy. So I will start the first half of the presentation, actually 2/3 of the presentation, are regarding a research project that I've been coordinating in 3 years. Actually, it took a little bit more than 3 years to run. This project was funded by the Italian government, and the goal of the project was to evaluate the seismic safety of buildings that we design according to the most current, most advanced, updated Italian construction code in Italy, which is very similar to Eurocode 8. Those who are familiar with structural engineering here in the audience know that we design for seismic resistance of buildings with ground motion, which have a specific probabilistic meaning. It's uniform across all over the countries, but the resulting seismic risk of structure, of code-conforming structure, is not known by the engineer that is designing the building. So the government asked us to evaluate that. It was a very large research project involving experts of building design and modeling all over the country. You see here all the university and research institutions involved in the project. The map that you see here is the probabilistic seismic hazard map. So it's the peak ground acceleration with 475 years return period all over the country, which we use for design. This is the basis of the code. So we select a value here, which is the same probabilistic meaning all over the country. The ground motion is lower in the sites with lighter colors, and it is larger at the most hazardous site in the Apennines, but the probabilistic meaning is the same. So we ensure uniform seismic hazard when we do design. So to run this project, we analyze 5 structural typologies: reinforced masonry structures, reinforced concrete structure, precast reinforced concrete structures, steel structure, base isolated structures. We designed these structures at 5 sites: Caltanissetta, Napoli, Roma, L'Aquila, and Milan. Different hazard levels, so different seismicity at these sites. But I will show you the results only for 3 sites, because this suffices to explain the results. So the 3 sites are Milano, Napoli, and L'Aquila. So Milano is low hazard, Naples, where do I live, is mid hazard, and L'Aquila is high hazard, according to the design ground motion hazard map in the country. Very quickly, let's go to the structures that we have been designing. These are the kind of masonry buildings. They are new, so code-conforming masonry building, although in Italy the most of the building stock is made of not code-conforming masonry buildings, but very old masonry buildings. So these are those that we have been designing. So there are 2- and 3-story masonry buildings. Regular and irregular in plan, and regular and irregular in elevation. So you see 2 example models, different plan views. So we designed this building and modeled it. They were designed for the specialists here in the audience with the simple building, equivalent frame, and linear static approaches. So all design approaches that are allowed by the Italian code for designing masonry buildings. Each of these buildings, the same type, so same number of stories, and the same plan view, was designed at each of the sites that we show. So, but the resulting buildings, of course, are different because the seismic hazard level that we use in design is different among the 3 sites. Regarding the reinforced concrete buildings, we designed 3, 6, and 9-story moment-resisting frame buildings. Here I'm showing only the 6-story model. This is the plan view of the reinforced concrete building, which was always the same regardless of the number of stories. So 3, 6, and 9 stories. Again, you see here only the 6-story. For the 9-story, we also consider moment-resisting frame coupled with shear walls, so different kind of structural configuration. We designed these buildings at all the sites, so low, mid, and high hazard in Italy. And for each building, we analyzed 3 different buildings. So the first one was what we call the bare frame. So naked building as a reference. But we also analyzed the completely infilled buildings with infillings that close the building, and also the pilotis building. So when you have infillings from the second story to the top. Of course, we have a model for infillings, such as a nonlinear model for buildings. I will not give the details. And of course, the nonlinear model for infillings, when we analyze the building, consider openings and the possible presence of opening. The model analysis was the only one design approach used, because it's the most common in engineering practice for this kind of buildings. The behavior factor for who is interested was 3.9. So it's kind of low ductility according to Eurocode 8. This was constant all over the country, regardless of the seismic culture. Precast reinforced concrete buildings, we considered the most common precast buildings that we have in Italy, so they are industrial buildings. So kind of regular reinforced concrete columns and pre-stressed reinforced concrete beams. So they are one story, one bay in this direction, industrial buildings, precast. And you see here a table which shows the different geometrical configuration that we analyze, that we design and then we analyze. So we analyze buildings with two different heights, although it's always single story, and two different dimensions in plan and in this and in this other direction. And these are the kind of buildings we analyze. More than 20 structures. Of course, each structure, again, same configuration, was designed for different hazard level across the country. We also consider steel industrial buildings. Steel industrial buildings are of the same shape of the precast reinforced concrete building. So one story, one bay in this direction. The geometry is very similar to that of precast reinforced concrete buildings. Of course, the structural system is different because we had to brace in this direction the building to have enough resistance. I want to stress that you see here the wind loading in particular, snow and wind loading in particular for this kind of buildings, because the steel buildings in Italy are, in general, but in these cases that we design are so light that the lateral force that rule design is not the earthquake, but is wind. So the most of the lateral resistance in this building was given by the wind load, not the earthquake. Finally, we analyzed base isolated buildings. What we did is basically take the reinforced concrete building designed in the other typology in the Milan site, because this is the lowest hazard. We put this building in L'Aquila. L'Aquila is the most hazardous, one of the most hazardous sites in the country. And of course, this reinforced concrete building was not adequate in terms of earthquake resistance. So we base isolated that. This is the way we constructed base isolated cases in this project. And we consider three different isolation systems. High damping rubber bearings, which is very common, but not that common alone. So we also consider a more common system, which is high damping rubber bearings coupled with sliders. Second system. And then we analyze third configuration of base isolation, which is made of friction pendulums. So this is a summary of the cases that we analyzed. You see here a matrix of the different typologies and the sites. They are ordered in terms of seismicity, of seismic hazard. So least seismically active from the most seismically active, different typologies, all the cases that we analyzed. So about 50 cases of reinforced concrete structures, about 80 cases of unreinforced masonry structures, about 24 cases of precast reinforced structures, same for steel, and some base isolated cases. You don't see base isolation at the least seismically active sites because we consider that it's not generally useful to base isolated structure in Milan, where the seismic hazard is very low. So what do we mean by seismic safety? So we estimated what we call the annual failure rate, so the expected number of earthquakes per year that are able to fail the structure. But we have to define a failure criterion. This is a little bit figure for specialists. So this is basically a pushover curve of each building that we design. So a kind of constitutive relationship of the building. On this axis, there is the what we call engineering demand parameter. It's a kind of measure of the earthquake performance of the building. For example, the roof displacement of the building during an earthquake. And on this other axis, there is the base shear. So there is the force that the structure gives in opposition with respect to that applied to the earthquake. So this is a constitutive relation of the building. And we define global collapse when we get a roof displacement so high that it corresponds to a reduction of the strength of the building, so the maximum force the building can oppose to the earthquake, a strength reduction of 50%. So if the displacement is larger than that, we consider that global collapse. Of course, this is, we believe that we can observe global collapse, but unfortunately, numerical models do not allow to do anything better than that. So we have to somehow have a surrogate definition of global collapse, and this is the way the research team came up with a failure criterion in terms of global collapse. So we believe this is kind of life-threatening condition for the occupants of the building. Okay. Actually, we consider also another failure criterion, but I have no time here to discuss it. So the kind of damage that prevents functionality of the building after the earthquake, but I will stick showing you the results of global collapse. Okay, so the goal is for all the buildings that we've been seeing, computing the annual failure rate. So the expected number of earthquakes at the site where the building is located that are able to induce global collapse to the building. This is the number we want to estimate. This is a measure of structural safety. We compute that with the state-of-the-art research approach, which is not very fancy. It's just application of total probability theorem for those who know that. And so it's computed separating this calculation in two terms. A first term, which we call probabilistic seismic hazard, which is only depending on the site. And it's basically in the form of a curve that for each value of a ground motion intensity measure, so all possible earthquake intensity that a site can experience, the annual rate of exceedance of that ground motion intensity measure. So it basically is a measure how hazardous seismically a site is. So this is only site dependent. And then we have what we call seismic fragility of the building. So for any value of the ground motion intensity measure, the same that we have here, how likely is failure going to occur given that ground motion intensity measure? This is depending on the building, but also to some extent on the site, and we call seismic fragility. When you integrate the two, you get the annual failure rate, the expected number of earthquakes per year that are able to fail the structure. So let's look at this term first. So we compute the hazard. Actually, our code is based on probabilistic seismic hazard analysis, but we had to recompute that for the purposes of the building. And you see here the different 5 sites that we consider. What we use, the polygons that you see here is the official seismic source model for Italy. So each of these polygons is characterized in terms of annual rate of occurrence of earthquakes and some magnitude distribution, and this is the official source model for Italy, and we compute the hazard according to that. And you see here an example of the results for the 5 sites. So you have peak ground acceleration, maximum acceleration that ground can experience on the rock, and you see here the expected number of earthquakes per year that are going to exceed each value that you read on this abscissa. This is hazard curve, what we call hazard curve. You can see here that actually, as I told you, Milan is the least hazardous because for each specific value, Milan has the lowest rate of exceedance, and L'Aquila is the most hazardous because for each PGA value, L'Aquila has the highest rate of exceedance of that value in 1 year. And Napoli is in the middle, is mid-hazard side. This example of the results that we use to compute the failure rate. Okay. Then these are the same curves that you have seen in the previous figure, just in logarithmic scale. Then we selected, according to the hazard, some ground motion records. These are actual records, acceleration recorded in earthquakes. We use that to compute the fragility of the building. We build up numerical models of the building and run some simulation with some ground motion that we selected compatible with the seismic hazard that we probabilistically evaluated the previous slide. But these are details. We did with the conditional spectrum approach. So what we did, for each of the buildings that we have been designed, all these structures that you have seen, we build up a nonlinear numerical model. So structures one of the problems that we have structures are so big, so different to each other that we cannot rely much on experiments. So we have to run numerical simulation to evaluate their behavior during earthquakes. So for each of the building, here you see an example of the reinforced concrete building. We build up a three-dimensional numerical model of the building and subjected it to ground motion. The ground motion that we selected according to the hazard for each site. We selected different ground motions for different intensities because we want to evaluate the performance of the building, to evaluate the fragility at all possible intensities. So for each possible intensity of the earthquake, we selected different ground motion. You see increasing intensity. And we evaluated the response. We call that multi-stripe analysis. For each intensity, we use several simulations to evaluate the displacement of the building to see how bad the performance was or if failure was going to occur. And we estimate the fragility with some state-of-the-art relationship. These are the results. And basically, this basically concludes the presentation, the first part of this presentation. So each color represents a building typology. And you see here the three sites I was mentioning: Milan, low hazard; Naples, mid hazard; L'Aquila, high hazard. And you see, regardless of the typology, the failure rate is increasing, which means that although in Italy we are designing with the ground motion with the same return period of exceedance at each site, we don't ensure uniform safety. So we have uniform hazard in design, but we don't have uniform safety. And the worst is that the safety is decreasing as the hazard increases because the failure rate increases. We were a little bit, we knew that something we were going to observe. We were a little bit surprised that it was the effect because the difference in failure rate increases as the hazard increases by orders of magnitude. So this is 10 to the minus 5. Actually, in Milan, the buildings are so resistant to earthquake that we could only estimate that the failure rate for many of them is below 10 to the minus 5. Actually, the number is way below the screen, but we could only estimate that. While if we go with L'Aquila, we have something like 10 to the minus 3 or 10 to the minus 4. It was very interesting to us. You see also some dishomogeneity of failure rates at the same site for different typologies. This is likely due to difference in design detailing different typology, for example, Masonry buildings or reinforced concrete buildings. I have to say that it's also dependent on the fact that the nonlinear modeling of this building is not uniform across the typology. So there's also something related to the research, the way we conducted the research. But in any case, the primary result is that this is increasing by orders of magnitude as the hazard increases. I will try to explain you why. There are two reasons we found that this happened. So these are the 6-story bare frame reinforced concrete building in Milan, in Naples, and in L'Aquila. So three different buildings of the same configuration, bare frame. What you see here is the backbone of the pushover curves in terms of single degree of freedom system. It's basically the constitutive relationship of the building I've been showing previously. And you see that this is the same scale. So you see that, of course, in L'Aquila we design larger strength building and lower strength in Milan. This is reflect our design for different hazard levels. So what we can do is plot this same constitutive relationship in terms of this is this roof displacement basically, and this is spectral acceleration, so ground motion acceleration. We can plot that in non-dimensional format. It's the same drawing of the previous slide, but basically this is what we call ductility. Is non-dimensional displacement, and this is non-dimensional acceleration. It's what we call strength reduction factor. So these are the same constitutive relationship put together in the same non-dimensional scale so that we can compare. What you see here is the design spectrum for these three buildings. So you see that although we designed for this one, and this one, this structure, so we should expect the same intersection point. To the three, it is not. In Milan, we have a performance point which is in the elastic range in Naples, non-elastic range only in L'Aquila, which means that the Milan building is, by design, oversized with respect to the required hazard. How would that be possible if we design for probabilistic hazard? It's because of minimum requirement of the code. In the lowest and mid-hazard sites, the code, even the required size of the building members is small because the seismic hazard is small. The code does not allow to go below some threshold. So the result is that the Milan building is relatively oversized with respect to L'Aquila because the site minima are not allowed to go below that. This is one of the two reasons why we observe this increasing trend of failure rates. But there is another one. Another one is that when we design, this is the largest, the red spectrum is the largest ground motion that we consider. We accept, we don't control the behavior of the building beyond the design spectrum. And the point is that in the high hazard site, the expected ground motion exceeding the design spectrum is disproportionately larger in L'Aquila. So not only that in a high hazard site the design ground motion is large, everything we don't control after the design ground motion is much larger in high hazard site than in low hazard site. Basically, it depends on the fact that the slope of these curves in Milan and Naples is not the same. So are much less steep, the curves in high hazard site, which means that if you take the ratio of PGA with 10 to the minus 3 exceedance rate, and you compare with that with 10 to the minus 2 exceedance rate, this ratio is much larger than if you do the same exercise in Milan. So the design ground motion and what happens after the design ground motion that we don't control in design is much worse in L'Aquila than in Naples, in Milan and Naples. This is the second reason why we see this observing increasing trend. Okay, this is what we found in terms of new buildings, and there's a debate now in the government whether we should do something, because what we can say is that we are okay with these numbers. So we said that we provide a minimum safety in high hazard sites, and in the others is higher than that, so we can stay with that. Or we want to lower that or push this up so that we have a uniform risk. This is the debate that is going on in the government from the technical point of view, to see whether we should change our earthquake resilience policy for new buildings. But I think this is a debate that should go at the European level, because the Italian code is very similar to the Euro code. Now I'm showing you very briefly, very briefly, the policy that we have in place for existing buildings, because the vast majority of the building stock in Italy is not designed according to the latest code, which was enforced 10 years ago and updated last year. They are much older buildings designed with obsolete code or with no earthquake code at all. They are very old buildings. So we have some policy in place. This is not my work. It's work of my department, partially work of my department at the university, but I will show you anyway because I think it's relevant. So this is a law, this is enforced now in Italy, which assigns a earthquake-resistant class to the building, which is the same scale as we do for energy efficiency. So we have, I think there are 8 classes of risk, which is the same class of energy. And if some citizen prove that it can upgrade this building, moving from the current class of the building up to 2 steps above, 2 classes above, he gets to 70 to 85% tax deductions on the retrofit intervention. So this is kind of way we call that SISMA bonus to promote seismic retrofitting as alternative of public and industrial, not public, private and industrial buildings in Italy. Again, it's not my work, and everything can be improved technically, but it's very interesting because it's the first time that I see worldwide, including US, where this is the seismic class, efficiency seismic class of the building is estimated, evaluated in terms of expected annual loss. So basically the expected annual loss is the failure rate multiplied by the value of the building. So it's the first time that the seismic value of the building is assigned of actually very risk-based metrics. So for each building, if someone wants the tax deduction, has to evaluate the expect an annual loss of the building, and then prove that the retrofit intervention can improve by a factor of 2 classes. And this is done by the expect annual loss. So what the law, which is enforced, says? So it assigns a percentage of reduction of reconstruction cost to different possible damage levels of the building based on what we do expect for new buildings. So we know how much some level of damage is in terms of reconstruction cost for code-conforming buildings or for new buildings. And if we can prove that we can move the expected annual loss, so this is the exceedance rate, this is the reconstruction cost of an existing building, the red curve, to something similar or better than a new construction, then we have ante-operam and post-operam plus modification, and then the citizen can get 75 to 80% deductions on the retrofitting intervention. And that's all. I think that the recommendation that you have here, that I've been reading on the declaration of the World Construction Forum are very much consistent with what I've been showing, so I have nothing more to add. Thank you very much.